Okay, so in section 2.2, the second part, finding limits algebraically, we had just seen how to find a limit with direct substitution. If the x value that you're approaching is in the domain of the function, then you can just plug in that x value and that'll give you the limit. But we are also very interested in what is going to happen if the x value that we're approaching is not in the domain of our function. Okay, because then we can't just plug in that x value. The function would be undefined, and that wouldn't really tell us anything about the limit. So what we're going to do here is use this property. Okay, if x equals c is not in the domain of f of x, we can say if we have our f of x and we can find a function g of x that's identical to f of x when x does not equal c. Okay, so these two functions are the same thing except at x equals c, okay? So they're almost identical. So if we can find that g of x function that satisfies this, then we can say the limit as x approaches c of f of x is going to equal the limit as x approaches c of g of x, okay? As long as those limits exist. Okay. As long as the limits are actually a thing. Okay. So what this could be helpful for is instances like the very first example in section 2.2. So it's been a little while since we looked at that. 2.2.1, here we go. All right, so here was a function, a rational function right here. And we wanted to look at its behavior near x equals 2, but x equals 2 was not in the domain of that function. It made the function undefined. Okay, so we graphed the function out here and we could see, okay, there's the hole when x equals 2. Okay, it's really not in the domain. But the function itself has a familiar shape. It looks like just a parabola with a hole in it. All right, so what our new property is saying is that if we can find the equation of this parabola without a hole in it, it's almost identical to our original function, with the exception of that hole. So if we can find the equation of that parabola, that's our new function g of x, and we could use it to find the limit. Okay, so let me just draw kind of a quick little picture of that, representing what we were doing there. Okay, so we had a situation like this with a hole in it. That was like our f of x. Then we want to say, can you find g of x? Which would look like basically the same exact thing, but without a hole in it. Because then that g of x would help us find the limit, because we could actually use the point that fills in that graph. All right, so for example here, we're going to practice that. We are given the function f of x equals x squared minus 9 over x minus 3. We want to find a function g of x such that f of x equals g of x when x does not equal 3. Okay, so you might note there that our point that we're interested in, the x value that we are looking at, is going to be seeing what's going on at x equals 3. Okay. That is decidedly not in the domain of our original function f of x. Okay, if you try to plug x equals 3 in there, you're going to get a 0 in the denominator, and that would be a problem. It's undefined. So let's see what this function actually looks like. We can use a little bit of technology to assist us on this. All right, off to the side here, I've written our f of x expression. This was f of x, x squared minus 9 over x minus 3. And then OneNote, which I'm working on, has some really handy dandy little math tricks here. It will let me write in the equation and then it'll graph it, which is pretty fabulous. And I can put that graph in our page here so we can look at it. Cool. Okay, let me drag this over into the main part of our document. All right, resize it a little bit and drag it around right over here. So this is the graph of f of x. Now, you might notice that this graph, or these graphs made by graphing calculators or technology in general, are not always super great at showing you undefined places. So notice that we know f of 3 is undefined. All right, if we tried to plug it into our function, getting that 0 denominator would be a problem. We know that there really should not be a point where x equals 3 on our graph. So what is really happening here, because notice 1, 2, 3, x equals 3 is right here. The calculator, the automatic graphing on OneNote, was not quite clever enough to put in a hole in the graph right there. Okay, so this is not exactly that line. It's a line with a hole. But what OneNote has essentially graphed for us is the g of x function that's going to match up and be identical to f of x, except at the point where that hole is. All right. Because yeah, those holes are so teeny tiny in reality that it's really hard for the calculators to be able to show them. Some of them can do a good job and they'll put in a hole for you, but yeah, not all of them will quite get that. Okay, so f of x looks like a line with a hole. And so we might say, okay, the line itself, line without the hole, can be g of x. Okay, and so then it's just up to us to determine the equation of that line based on the graph. And since it is actually a line, we can do that. We can look at the slope and we can look at the intercept. So our slope, using just a simple rise over run type of calculation, or you could pick 2 different points on the graph. I'm going to go rise over run because it looks like we rise 1 unit, run 1 unit. So slope of 1, so we'll have 1x plus our intercept, which is right here at 3. Okay, so our line without the hole is x plus 3. That is our g of x function. So g of x, x plus 3, looks exactly like f of x, x squared minus 9 over x minus 3, at every single point except when x equals 3. So when x doesn't equal 3, the two of them are exactly identical. And that's pretty cool. Okay, so we could definitely use this g of x in other calculations, in finding limits, all types of good things. Now you might notice something on here where there's a little shortcut going on. Okay, if you're kind of looking at x plus 3, maybe seeing how it relates to that original f of x function, notice that if we did some factoring and canceling, we could get that same result, okay? Because x squared minus 9 over x minus 3, you can factor that numerator. That is a beautiful little difference of squares right there. So you'll have x plus 3, x minus 3 for the factors. And then we'll be able to just cancel that x minus 3 factor right out and get x plus 3. Okay, so that is another way to find that g of x function. And then we can use that. So if we wanted the limit, as we approach x equals 3, we could say limit as x approaches 3 of x squared minus 9 over x minus 3. Okay, there's original f of x right there. All right, f of x. It's going to be the same as the limit as we approach 3 on the function g of x because of this property right here. Okay, we found that other g of x function that matches f of x. So that tells us that the two limits are going to be the same as long as those limits actually exist, which they do in this case. Okay, so we can say this equals the limit as x approaches 3 of g of x, which is just simple little x plus 3. All right, so there was the f of x part. Here is the g of x part. We're putting in our g of x function. And then we get to go back to that first idea that we looked at, circle number 1, direct substitution. Because now g of x, x plus 3, is a polynomial, and x equals 3 is in its domain. Okay, g of x is actually defined there. So we just get to plug in x equals 3 and use this property right here. That's what our limit will be. Okay, so we get to plug in 3 and we get a limit value of 6. All right, so that is good to know. One more little example here with factoring and canceling, because you don't have to go through this whole process with the graph and writing down, oh, this is a line with a hole, that type of thing. You don't have to do that every single time. So let's run one more example here real quick where we just factor and cancel. All right, so there's one example here, factoring and canceling. Here's another one. Okay, we are taking the limit as x approaches -2 of x cubed plus 8 over x plus 2. Okay, first things first, one thing you always want to check right off the bat is, can you use direct substitution? Because if you can, that's the fastest. But here, x equals -2, x approaching -2 there, we can't plug -2 directly into this original function. It would give us a 0 denominator. It's undefined. Okay, so we do actually need to factor and cancel here. Thankfully, this is set up to factor and cancel for us. One little thing you might want to refresh here, that numerator is a sum of cubes, x cubed plus 8, x cubed plus 2 cubed, and sum of cubes has a specific factoring formula to it. We don't come across it too often, but when we do, it's really handy. So here, the way x cubed plus 8 is going to factor is x plus 2 times x squared minus 2x plus 4. And then we have that all over x plus 2. So how convenient. We are going to get to cancel out those x plus 2 factors. And so we have the limit as x approaches negative 2 of x squared minus 2x plus 4. And it turns out that that right there, that's our g of x function that matches up to the original, except at the point where x equals negative 2. All right, our original f of x here has a hole where x equals negative 2. The g of x function over here is the same thing except with that hole filled in. So what that allows us to do is to actually plug in x equals negative 2 now. Direct substitution. So negative 2 squared minus 2 times negative 2 plus 4. So we are direct substituting. And we will get 4 plus 4 plus 4. Okay, we will get a limit of 12. Okay, and that is the final value. That's the answer for this original limit. Now, one more note there. Notice how in going from this step to this step, I stopped writing limit as x approaches negative 2. That is a really good thing to know notation-wise. When do we get to stop writing the limit thing? Because we often have to keep writing it over and over and over again, and it gets a little tedious. But you get to stop writing limit whenever you plug in the x value that you're approaching. So once you can use direct substitution, you get to stop writing limit. So stop writing the whole LIM business, x approaches c, whatever value c might be. So you get to stop writing that when you substitute. Okay, whenever you plug in the actual value that's being approached. Okay, so that's a good note on notation there.